All right, this is section 6.3 over linear functions. A linear function is a function whose graph is a non-vertical line, dot there, and can be written in slope-intercept form, which remember is y equals mx plus b, or as we talked about, you could write f of x equals mx plus b. Now, the reason that it has to be non-vertical is because if it's vertical, two things happen. First of all, it doesn't pass the vertical line test, so it wouldn't be a function. Although it's a line, it's not a function. And remember, by the way, if it was vertical line, it cannot be written in slope-intercept form. We'd have to write x equals a number, right? So that makes sense. We can't write it in slope-intercept form, so it wouldn't be a linear function. And then the second thing is that you'd have one x variable going to a whole bunch of different y variables, right? So we got a point there, a point there, a point here, there, right? All these different points. So it's definitely not one-to-one. So not only does it not pass the vertical line test, it's not one-to-one. So a vertical line is bad news. It's not a function, right? So these have to be non-vertical. They can be horizontal. Horizontal lines can be written in slope-intercept form. They just don't have a, slope is 0, but we cannot write a vertical line in slope-intercept form. So it says use the graph to write a linear function that relates y to x. Guys, we did this in chapter 4. This is going to be fairly easy for us, I would say. It's a good little review. But you can see these points make a line that goes right through there. And you can look at those points to find out what is the slope and what is the y-intercept. So I can see the slope is rising, let's see, 1, 2, 3, and running 1, 2. So that's 3 over 2. And I can see that the y-intercept is -3. So y equals 3 halves x minus 3. For example B, the line that these points would make, it's non-vertical, just like the last one, so it's definitely a function. And the slope is down 1 over 2, so y equals -1 over 2 x. And I probably should put that x, probably erase that, put that right in the middle where it probably needs to go. And then the y-intercept is -1, so -1 half x minus 1. And we could also use charts to write our linear functions. We can look at this chart here. You can see not only can you tell what the slope is, but you can tell what the y-intercept is. We can see that the slope is, the rise is decreasing, so we're going down 2, and then we're running +1, and you were seeing that same pattern throughout the chart. So our slope is going to be -2 over 1, or -2. And then our y-intercept is always when x equals 0, right? So if we have x equals 0, that y value is going to be our y-intercept. This is exactly what we were doing. This is going to be pretty much a review of everything we've done with slope-intercept form. You can also write f of x equals instead of y. I think your homework is going to have you write y, but you could write f of x for the function. And then here we are actually our rise is 0, right? You can see that's consistent. So we're not rising. And then we're running 1 each time. So then we write 0 over 1, and 0 over 1 is just 0. So this is a horizontal line, which is still a function, but it's not going to have a slope. So we're not going to have an x value because the m is 0. But you can see what the y-intercept is always going to be. It's 2, right? No matter what, y is 2. You can even see they gave you x is 0, y is 2. So this is the function f of x equals 2. Or you could write y equals 2. It is a horizontal line, which is still a function. Let's look at a couple more examples. You can see I gave you some more space here, which probably means we're going to need to show some work. And we can see that the x value being 0 is not given to us. So we're going to have to work a little bit to find the y-intercept. So for the first one, we can see that they're rising 2. It's +2. And then they're running 3. So we know the slope is 2/3, rise 2, run 3. And we need to try to get the x to be 0. So that's not going to be super hard for us, right? We can back up 3. If we go back 3, x would be 0. So we'd have to, obviously subtract 3 if we're going the opposite direction. And then if I back up here, I would be subtracting 2, going in the opposite direction, and that gives us negative 6. So if I put one more point on this chart, 0, negative 6 would actually be it. Oops. So my function would be y equals 2/3 x minus 6. So remember, if you couldn't see that, I have to back up to try to get x equals 0, you could always use slope-intercept form, plug in the slope that you have, which is 2/3, and then choose one of the points. Like this one here looks pretty simple. You could plug in 0 for y, you could plug in 9 for x, and we could find out what that b value really is. 2/3 of 9 is 6. Subtract 6 from each side, and you get b equals negative 6. So that makes sense. That's exactly what we got. So we have the b value, we have the m value, and that's all you need to write your linear function. All these functions in this section will be linear because that's what it's titled. Now, that method of backing up, right, like we used up here, is great, right? If you get some x values, you can just backtrack to see what x would be at 0 and find out what the y coordinate is. But for this next example, D, that's going to be a lot tougher for us to do. So I'm going to go ahead and stick with this method here because I know that's worked in the past for us. Remember, you can also use point-slope form. We learned that a couple chapters ago as well. So let's start off by finding the slope. We're decreasing 2 each time, and we are increasing 5 each time. So my slope is going to be rising negative 2 over 5. Now, I can pick any of the points they gave me, like this one here, for example. I can pick any of those points, and I can plug it into the slope-intercept equation. So y is negative 10, m is negative 2/5, x is 105, and I'm trying to find out what b is. So an easy way to do, obviously 1/5 of a number is like dividing it by 5. So if I did 1/5 of 105, it's like dividing it by 5, and that's going to give us 21. If I want 2/5, that would be another 21. If 1/5 is 21, then 2/5 will be 42, and it's negative, so this is negative 42. By the way, if that didn't make sense to you, write it off to the side, and you'll know exactly what I'm talking about, right? The 5 and the 105 are going to cancel, and negative 2 times 21 is negative 42. And then I can complete the rest of this. I can add 42 to both sides, and when you add 42 to negative 10, you get 32. So b equals 32. Why am I doing all this work right here? Because, well, the chart was not very friendly to me. It didn't give me anything near what my y-intercept was, so I had to do some extra work. But now I know my slope is still negative 2/5, and my y-intercept is now 32. So I have my function, just like I had my function right here for the last one. So we can write functions looking at graphs. We can write functions looking at charts as well. All right, this next example is plot the points from the chart on the coordinate plane, and then write the linear function for each of write the linear equation for each of the functions. So we've got 0, 150, which is right here, and then we've got 2, 125, right there. We've got 4, 100. Oops, I went wrong spot. 4, 100, right there. 6, 75, and 8, 50. So this is a linear function, and we can graph the line that looks like this. It's got a negative slope. In fact, we're going down 25 every time we go over 2. So I can either write my slope as down 25, negative 25 over 2, or I could write it as a decimal, negative 12.5. So my y-intercept, you can see, was right here at 150. That's the point they gave us, right? Anytime x is 0, we look at that and we say, oh, that y value is our y-intercept. So the function I can write is y equals negative 12.5x plus 150. And then for the second one here, I'm going to write the function rule beforehand. Let's see if we can do the function rule beforehand. We can see what the slope is doing. It's rising 5 every time we run 2. So my slope is going to be 5 halves. And if I backtrack this 2 more, that would be at 2, and that would put me at 10. And if I backtrack it another 2, that'd be 0, and that would put me at 5. So my slope, or sorry, my y-intercept is going to be right here at 5. And just to double check that, let's go ahead and plot the points they gave us. 4, 15, 6, 20, 8, 25, 10, 30, and 12, 35. And you can see if I continue this pattern, yep, we're right there on the y-axis at 5. So I can, this one's easy enough that I don't have to use slope-intercept form. I can actually just backtrack it to figure out what my y-intercept is, and then I can write y equals 5 halves, or 2.5, x plus 5. All right, next up, this says the table shows a familiar pattern from geometry. Remember, we did this geometry chapter at the very beginning of the year. It wants us to write a function that relates y to x, and then it says, what do the variables x and y represent? So we've got a circle here. X would be the radius, and when I plug in 1 for the radius, I get 2 pi for y, and I'm supposed to not know what 2 pi is yet. Could be the diameter, could be the circumference, could be the area. There's a lot of different things it could be. When I plug in 2, I get 4 pi. When I plug in 3, I get 6 pi. When I plug in 4, I get 8 pi. When I plug in 5, I get 10 pi. So it looks like what they're doing each time is they're timesing it by 2, right? And then they're adding pi in. Well, that looks a lot like our circumference formula, which is 2 pi r. So the circumference formula, 2 pi r, takes the radius, doubles it, which, by the way, is the formula pi times d, when you double the radius, and times it by pi. So this is the circumference. So x represents the radius, and y, in this case, is representing the circumference. Wants me to write a function, so my function is going to be, now in relation to x, right? So I can't use pi d because they're not giving me the diameter. I can't use that one. So it's going to be 2 pi r, but they're calling my radius x. So this is my function rule. And you can see, check it out, when we plug in 1, we get 2 pi. When we plug in 2, we get 4 pi, so on and so forth. Example B is a little trickier. Right, we've got a length of 4, we don't know what the width is, and we know the height is 2. And it's a rectangular prism. So when I plug in 1 for x, I'm supposed to get 28, and I'm supposed to know what 28 means. And when I plug in 2, I get 40, and I plug in 3, I get 52. So it's increasing by 12 each time. Right, so I can tell it's increasing by 12, so that would be the slope. And then the y-intercept is going to be, if I back this up another 12, okay, that would be the y-intercept would be 16. So there's my function. I can get that, but I'm supposed to understand what the heck y is supposed to be. So actually, if you mess around with this a little bit, you find out this is the surface area formula. Remember, the surface area formula for any prism is S equals 2b plus capital PH, where capital B is the area of the base and the capital P is the perimeter of the base. Now, because I don't know what this value is, I'm going to call my base the front side, because I at least know that the bottom of it is 4 and that this is 2. So let me go ahead and just plug this in and see if we get what we got up here. If you plug in capital B is area of the base, which is base times height, or 2 times 4, plus the perimeter. So the perimeter would be 2 plus 4 plus 2 plus 4. 2 plus 4 is 6, so that's 12. And then the height, which would be the distance between my two bases. So these are my two bases, right? My height is going to be x. And let's see what we get here. We get 2 times 4 is 8, times 2 is 16, plus 12x. And yep, that's exactly what we got up here. So our function formula is right. This y represents the surface area of the rectangular prism, whereas x represents its width. And I'm looking back at this last one, and actually it does say to relate y with x, so I need to scratch this out. We need to write y equals 2 pi x, so it looks more like the one we just wrote over here, up here, which I've circled like 17 times now. It looks kind of cool with all the different colors. Our next example says you're controlling an unmanned aerial vehicle, or UAV, for surveillance. The table shows the height in thousands of feet. So times each of these values by 1,000, all right, of the UAV after X minutes after you start its descent, which means it's going down, which is why you notice each of these are going lower and lower, from cruising altitude. Write a linear function that relates x to y, interpret the slope and the y-intercept. So we need to be careful here because this says it's measured in thousands of feet. So when it goes down 5, it's actually going down 5,000. And then we're running 10. So my slope, it'd be very easy to say, oh, it's -5 over 10, which is -1/2. Okay? But that's actually half of 1,000. Half of 1,000 is 500, right? So if I write it like -5,000, like it's supposed to be over 10, you can see that we're going to exactly get -500. So we got y equals -500 x. And then they give us right here, they actually give us what our y-intercept is. It's 0,65, but remember, that is supposed to be 65,000 feet. So what's throwing us off is the fact that all these numbers for the outputs are all measured in thousands. They're all thousands, so we have to times everything by 1,000. Now we can graph this, and we know the y-intercept is 65,000, which is right there between 60 and 70,000. And then going down 500 over 1 doesn't really make sense because 1 minute is going to be like right there, and it's not going to be very easy to graph. Plus, our chart is counting by 10,000s, not 500s. You can see on the y-axis here, we're going up 10,000 each time. We're not going up 500. So what I'm going to do is I'm just going to use the points they gave me as 10, 60. We put right here at 10 minutes. Whoops. At 10 minutes, we're at 60,000. And at 20 minutes, we're at 55,000. And at 30 minutes, we're at 50,000, so right there. And you can see our UAV is dropping all the way down, and at some point, after 80 minutes or so, it's going to be back on the ground if it continues this constant descent. And then it says, find the height of the UAV when you stop its descent after 1 hour. So 1 hour would be 60 minutes. So let's check to see how accurate we are. I'm thinking if I did this right, it's going to be at 30,000 feet because we know 60 minutes is 1 hour. But just to be sure, I'm going to go ahead and use the formula that I have here, the function rule, which is y equals -500x. Plus 65,000, just to make sure we did this right. So when it says after 1 hour, it's wanting me to plug in for the x variable, which is measured in minutes, and I'm going to plug in 60 right there, right? So -500 times 60 is -30,000, and then I'm supposed to add 65,000 to that. So -30,000 plus 65,000 is 35,000. And you can see that I was not quite as accurate as I wanted to be graphing. It should have been right around this area is where it should have met. So my line was not perfect by any means, which is why using algebra is always a good way to check. So it is going to be at 35,000 feet after 1 hour. Now let's compare two linear functions. You can see they're giving us one linear function as an equation here, and one linear function they're giving us as a chart. It says the earnings y in dollars, so y represents dollars, of a nighttime employee working X hours are represented by the linear function y equals 7.5x plus 30. The table, which is in green, shows the earnings of a daytime employee, and you can see what their earnings are. Which employee has the higher hourly wage? Well, the hourly wage would be their slope, right? What is their rate? So the slope or the rate. Now, clearly, you can tell the nighttime employee has a slope of 7.5. Now, in terms of money, that's $7.50 per hour. The daytime employee is earning $12.50 every hour, right? You can tell from the chart they're earning $12.50 every hour. So the daytime employee is working a lot, or earning quite a bit more per hour than what the nighttime is. So I'm going to say the daytime employee is definitely making more. Now it wants us to write a linear function for the daytime employee, or their earnings, so that to the number of hours worked. So we already have the equation of the nighttime employee. So now let's write this chart as an equation. So we said the slope was $12.50. That's what they're earning, or 12.5. I guess I don't have to write the 0 there. X plus, and then if I back this up $12.50 to get my x value of 0, I'll find out that my y-intercept is also 0. So I can erase my plus sign here, because, and that makes sense, that if a person doesn't work, right, if they don't clock in, they don't show up that day, they're not going to get paid. That's actually not true for the nighttime employee, because no matter what, they get paid $30. So that's kind of nice, even if they don't work any hours. So they get some sort of salary as their benefit to having to work at night, an extra $30. So it wants us to graph these. So for the daytime employee, they're starting at $0 if they work 0 hours, and they're going to go up 12.5 over 1. Now, hang on a second. Going up 12.5 is not going to be very nice. So I'm going to use this point right here. Going up 12.5 and over 1 is the same as going up 50 and over 4. And going up 50 over 4 is going to put us right around here. Okay, so right above 45. So about a third of the way, I suppose you would say, between 45 and 60. And for the daytime employee, the nighttime employee, they start at $30 and they go up 7.5. So instead of using 7.5 over 1, I'm going to modify this to, if they make $7.50 every 1 hour, they make $15 every 2 hours. So I can go up 15 over 2, up 15 over 2. This is just a system of equations, isn't it? And I'm getting them to intersect somewhere around here. That's what my answer would be, right? My system of equations would have an x and a y value right there, which in this case is the dollars for the y value and the hours for the x value. Now, because my graphs are not completely accurate, I need to find out where they would, what point do they make the same amount of money? So what I can do is I can solve this using algebra. I can use substitution and plug that in right there for y. So 12.5 equals 7.5x, or 12.5x equals 7.5x plus 30. I can subtract 7.5 from each side. I get 5x equals 30, and then I get x equals 6. So I can find out that it's at 6 hours, and I was a little off, but not by much. Not by much. So my x value is 6. And then if I plug that back in, I can find out what my y value is, which I'm thinking is like $65, $70, $72 maybe. So if x is 6, I can plug that in right here for x. So 12.5 times 6 is 75. So yeah, it's not quite accurate. I kind of knew I was off anyways, right? So 6 and 75. So 6 hours, $75 is where they both will intersect. So if you are a daytime employee, you will not be earning as much as the nighttime employee because, if you work under 6 hours. You can see from let me highlight this for you so you can see what I'm talking about. When you are a nighttime employee, you are going to earn more than a daytime employee because you're earning more, they're starting at 0. And then 6 hours is that break-even point, right, where you both be making the same. And then if you work after more than 6 hours, the nighttime employee is earning less, and then all of a sudden the daytime employee is earning more. So that 6 hours is our key, right? If you're going to work over 6 hours, which most people do in a workday, then the daytime employee is actually going to make a little bit more money with nighttime. If you're working under 6 hours, then the nighttime employee will actually make more. All right, so that was the end of the notes. We are done with the instructional part. This is all homework questions. I thought I would do quite a few homework questions with you, and I mean quite a few. There's a bunch of different homework on here. So let's get started with number 13. It says the graph shows the percent y in decimal form of battery power remaining X hours after you turn on a laptop. You can see that as the longer the laptop is left on, the more the battery drains. This is a negative slope. And it says write a linear function that relates y to x. So I can see that my y-intercept is 1. So I know my b value is 100%, right? And it's going down 0.2 and over 1. So it's going down 0.2 over 1, which is the same as just negative 0.2. So my my slope-intercept equation is going to be y equals negative 0.2x plus 1. Part B says, interpret the slope, the x-intercept, and the y-intercept. So let's read this in as we go. It says, the slope indicates that the power decreases by blank percent per hour, which we said was a negative 0.2, which is 20%. So it decreases, there's the negative, 20% per hour. The x-intercept indicates the battery lasts how many hours? Well, the x-intercept's right there. So on a full charge, it'll last 5 hours. The y-intercept indicates the battery power is at, right there, you can see 100% when you turn on the laptop. Part C, after how many hours is the battery power at 75%? They want you to plug in 0.75 for the y value. How do I know that they want us to plug that in for the y value? Because that's where the percent in decimal form is, right? That's where the battery power is. So I can take our function that we wrote, write it up here, y equals negative 0.2x minus 1, or plus 1, and I can plug in 0.75 because that's what my battery power is going to be at, and I can see how long it'll take me to get there. So start off by subtracting 1 from each side. That gives us negative 0.25 equals negative 0.2x. And that is 1.25. So x equals 1.25 positive, and that's the number of hours. So just over an hour, 0.25 would be a fourth, right? So 1 1/4 hours is actually 1 hour and 15 minutes, but it wants it in hours, so I can just write 1.25 hours, and I'll be at 75%. All right, number 14 says, you and a friend race each other. You give your friend a 50-foot head start. The distance y in feet your friend runs after x seconds is represented by the linear function y equals 14x plus 50. The table shows the distances you run. So you're comparing two functions. One is given to you as an equation. One is given to you as a chart. That's kind of the whole point of this whole section, is that you can look at these different ways of representing functions and compare them and see who's got the better slope, who's got the better y-intercept, all that stuff, or fastest or whatever. So it says who runs a faster rate. And what is that rate? That's going to be the slope. So I can tell that my slope from my friend, from their equation, is 14. So that's 14 feet per second. Because it says y is feet and it says x is seconds, and we know slope is y over x, so that's 14 feet per second. And then for the chart here, I can see that we're going up 38 every 2 seconds. So if we're going up 38, if we're moving 38 feet every 2 seconds, that would be the same as moving 19 feet every 1 second, right? So their rate is 19 feet per second. Or that's actually our rate. It says we, The table shows the distance you run, so that is your rate. So who runs the faster rate? You. And the rate is 19 feet per second. Part B says, write a linear function that relates your distance to the number of seconds. Okay, so we don't get that head start, right? Our friend got a 50-foot head start, which is why their equation is y equals 14x plus 50, because they have a 50-foot head start. Their initial value is 50 feet ahead of where we are. We did not have that head start. So actually, if you go down 2 and down 38, you're going to be at 0, 0. So ours is a direct variation. Our equation is y equals 19x plus 0, or just 19x. We don't get that head start, so that's what goes down there in that box, just using the slope and knowing that our y-intercept value is 0. All right, the next part of that problem wants us to graph, I believe, both of these lines. So I wrote down the equations of our friend and then our equation, which was y equals 19x. And so we have a y-intercept of 50 for our friend. They get the 50 feet head start, but they're moving slower than we are, which is probably why we gave them a head start. They're moving 14 feet every second. Now, graphing 14 feet every second is not going to be very nice. So what we can do is we can modify this slope. We can modify it by timesing 14 by 5 and timesing 1 by 5. And that means that moving 14 feet every 1 second is the same as moving 70 feet every 5 seconds. So if I add 70 to 50, I'm going to be at 120, and that's going to be 5 seconds later. So that's the point right there. And I went ahead and graphed that line for us. Your big ideas will do a much better job than what I did. And then for our slope, which was 19 feet every 1 second, if I times that by 5, 19 times 5 is 95 feet every 5 seconds. So I'm just modifying our slope so it fits this scale here. So I'm starting at 0. And I'm going to go up 95 over 5, which puts me right here. And I went ahead and graphed that line too. So you can actually see that our intersection is right here at 10 seconds. After 10 seconds, I will catch my friend, and then after 10 seconds, remember my line's the red line, after 10 seconds, I will now be in the lead, and my friend will be behind. Before 10 seconds, my friend will be in the lead, and I will be behind because they had the head start. So part C says, for what distances will you win the race? And that would be for anything after 10 seconds. You catch up to your friend after you run 10 seconds. Oops, take that off highlighter. After 10 seconds, so you will be ahead of him for any distance greater than, that would be, let's see, 10 and 190. That was right there at 190, right? So that would be, boom, right there. And I can double check that. I know Big Ideas makes it simple, but I can double check that by setting both these equations equal to each other, using substitution, plugging y in for y, subtracting 14x from each side, dividing by 5, and you can see it is 10 seconds, and if you plug 10 into this equation right there, it's 190. So you can see the intersection point is at 10, 190, and that's the answer to the questions down below. All right, more homework problems. Number 15 here says the number of calories burned y after x minutes of kayaking is represented by the linear function y equals 4.5x. So if I'm kayaking, I'm going to burn 4.5 calories, because that's what y is, every 1 minute. All right, so that's for kayaking. It says the graph, though, the graph shows the calories burned by hiking. So if I look at this graph, it's hard to be completely accurate with what that value is after 1 minute. So what I'm going to do is I'm going to use this value right there, which is a perfect intersection. And you can see that you're burning 30 calories after working out or hiking for 5 minutes. So 30 divided by 5 is 6 calories per minute. So that is for hiking. Which activity burns more calories per minute? Well, now we can tell it's hiking. Okay, by how many more calories do you earn for hiking, or do you burn for hiking than you do for kayaking if you do them both for 45 minutes. So if you're burning 4.5 calories for every 1 minute, then after 45 minutes, 4.5 times 45 is 202.5 calories for that 45 minutes if you're kayaking. Obviously, hiking is going to be more than that if we are working out, if we're hiking for 45 minutes. 45 times 6 is going to give us 270 calories. So if I subtract 270 minus 202.5, that gives us 67.5 more calories would be burned if I was hiking for 45 minutes versus kayaking for 45 minutes. Number 16, you and a friend are saving money to buy bicycles that cost $175 each. So again, we're going to compare two different things. We've got the amount of money in dollars y, so y is dollars, after x weeks is represented by the equation y equals 5x plus 45. The graph, so this is you, the graph shows your friend's savings. Who has more money to start? Well, boom, right there when it says start, that's the y-intercept. That's the initial value. So our y-intercept is 45. We already had 45. Our friend, their y-intercept on this graph here appears to be 15. So we have more money to start. You have, I think it says you have. Okay, you have more money to start. And then it says, who saves more per week? Well, that's the slope. So our slope is $5 per week, and our friend's slope, let's see if we can find perfect intersection points. I don't see any perfect intersection points, so I know this is 0, 15, and I can use this to help us find out what his slope is. We can do 39 minus 15, which is 24. And then we can do 3 minus 0, which is 3, and that means his slope is 8. So he's saving $8 per week. So we are saving $5 per week. They are saving $8 per week. So our friend is saving more money per week. So example B, or part B, says, who can buy the bicycle first? Explain. Your friend reaches $175 after blank weeks. You will reach $175 after blank weeks. So we have an equation that we can write for both of us. So for us, we already have our equation, right? Our equation is y equals 5x plus 45. And y represents our money, right? Well, it costs $175, so we can plug that in for y. And that will tell us, if we solve for x, how many weeks it will take us. Well, if you subtract away the $45 we already have, that's $130 more that we need. And if you divide 130 by 5, 130 divided by 5 is 26. So x is 26 weeks. It will take us 26 weeks. So did ours first, so that goes right there. Now our friend's equation, their y-intercept is 15, their slope is 8, so their equation is y equals 8x plus 15. I'm going to plug in 175 for them. Subtract 15 from both sides. Divide by 8, and that gives us 20. So our friend will earn it in 20. Even though we started with more money, they're saving $8 per week to our $5 per week, so they will catch up with us, and therefore our friend can buy the bicycle first. Gosh, writing with this really stinks. Friend will buy the bicycle first. All right, number 18 says the table shows a person's annual salary Y in thousands of dollars. Okay, so this is in thousands, so add 1,000 to all of these. After X years of education after high school. So someone who goes straight into the workforce is going to average 28. Someone who goes to 2 years of college, 4 years of college, 6 years, and even 10 years of college. It wants us to graph this data. Okay, so we go ahead and graph that. 0.28 puts us right here, and then 240 would put us right there, and 452 would put us right here, and 664 puts us right there, and then it skips to 1088, which is right up here. You can see that the point we skipped would have been right there. So this then is our line. So they want you to determine what the value or how much money we're making every 2 years of education. So you can actually see that we're increasing by $12,000 every 2 years. Well, 12,000 divided by 2 is 6,000 per year. Right? So every 1 year is going to give us an extra $6,000 of our salary on average. So $12,000 for every 2 years. The next question wanted to know someone who works or who goes to school for 8 years, what are they going to be making? So that was the point that we skipped, right? So we can actually look at the graph, and it was right here at $76,000. Right? That's what would be right between 64 and 88 would be 76,000. So that's the next question. So part C then says find the annual salary of a person that has 30 years of education beyond high school. So going back and looking at the chart, we can actually see what our slope is and what our y-intercept is. I already mentioned that our slope says that per year, remember, it's $12,000 for every 2 years. So our slope is $6,000 per year. So y equals 6,000. And then our y-intercept is 28,000. And that's what it starts at. Remember, we have the x value of 0 and the y value of 28,000. So if you go to school for 30 years, x was the time, you plug in 30 for x, and 6,000 times 30 is 180,000 plus 28,000 gives us $208,000 per year. And it asks us if this makes sense, and absolutely no, it does not make sense. It is not realistic for anyone to go to school for 30 years. I mean, heck, you work for how long? I mean, come on, 30 years of education, you would hardly have any time working by the time it's time for you to retire. So this does not make sense. Yeah, this does not make sense. So this chart only holds up so long, and then at some point people just don't go to school for any longer than that. All right, so this is not only the end of section 6.3, but it is the end of all the homework problems I'm going to do with you. So if you have any more questions, please let me know.